This is Chapter 4, Section 2, and we're going to talk about the quantum model of the atom today. That is going to be our fifth and final model that we talk about, which is also going to be the modern day model of the atom. In Section 1, we talked about light acting as a wave and light acting as a particle. Now we're going to move on and talk about electrons acting as waves. And in this first part, I'm going to highlight the important stuff here. Louis de Broglie, he suggested that electrons be considered waves confined to the space around the atomic nucleus. So you at least need to be familiar with his name and a scientist that is given some credit to the modern or quantum model of the atom, de Broglie. Again, we're moving on from light and we're moving in the photons that were there to electrons acting as waves. Skipping over a few things there, we're going to go on over to the Heisenberg uncertainty principle. And this first part here, you don't have to worry about it, but I do want you to write down the definition for the Heisenberg uncertainty principle, and it states that it is impossible to determine simultaneously or at the same time both the position and velocity of an electron or any other particle. So we're going to talk about the electron. De Broglie says electrons actually travel in a wave-like pattern. Heisenberg is saying you can't know the position and speed or velocity of an electron at the same time. Electrons travel at nearly the speed of light. So now if you were talking about you have your nucleus here and electrons are traveling around it, instead of electrons traveling in a nice circular pattern or orbits like what we finished off with Bohr's model, electrons are actually going to travel in a wave-like pattern around the nucleus. Okay, I know that looks more like an amoeba, but work with me. So they are going to travel in a wave-like pattern around the nucleus, and because of this and their very fast speed, it is going to be hard to know where an electron is located. On this slide, your more important parts are going to be that bottom section talking about the quantum theory. So the definition for quantum theory, it does describe mathematically the wave properties of electrons and other very small particles. And the title of this slide, the Schrödinger wave equation, he did have an equation coming up trying to figure out, can we at least somewhat predict where these electrons are going to be? We're not going to work with his wave equation, but at least there's another scientist's name you should be familiar with. So the quantum theory is based on a mathematical equation that looks at the wave properties of electrons and other very small particles. Electrons do not travel around the nucleus in these neat orbits, again, the way we thought Bohr had stated. Instead, they're going to exist in regions called orbitals. And there's your definition for orbital. Orbital is a three-dimensional region around the nucleus that indicates the probable location of an electron. Again, the probable location of an electron. And now we're going to get into how do we give an address to where we think an electron is located. And to do that, we're going to go ahead and jump into quantum numbers. Quantum numbers specify the properties of atomic orbitals and the properties of electrons in an orbital. And we're going to give you details of 4 different quantum numbers. This is just like trying to give you the address to your home. If I were going to write out the address and send you a letter, I would need your street number, your street name, city, state, zip code, some combination of all of that, but at least 4 major pieces of information so that you can get some mail. Electrons are going to be the same way. We're going to give them 4 specific quantum numbers so that we can try to determine where these electrons live. So starting off, first quantum number is the principal quantum number, and it is symbolized by the letter N. I'm going to be adding a lot of notes here for the different quantum numbers. Make sure that you get all of these added in, and we'll try to simplify it in one slide before we're finished today. So the principal quantum number represents the main energy level occupied by an electron. So again, I'm going to go back to just the very simple Bohr model. There's my nucleus. And if we were to just draw out simple orbits, I know that we've moved on to orbitals, that very first one is going to be the first energy level, n equals 1. The second is n equals 2. The third one is n equals 3. And you can keep moving out from there. So n can be a whole number starting with 1, 2, 3, 4, and so on. The lowest energy level and the lowest amount of energy associated with it is that energy level 1 located closest to the nucleus. And electrons want to be as close to the nucleus as they can in the lowest energy state that is available to them. And we will get into how many electrons can actually live on each of those different energy levels. But starting off, principal quantum number represents your main energy level. We use the symbol n to represent that, and it is some whole number starting with 1, and the further they are from the nucleus, the higher the number will be. The next quantum number is the angular momentum quantum number. The symbol that we use is supposed to look like a cursive L, and it indicates the shape of the orbital and the sub-level that your electron lives on. So principal quantum number is your main energy level. Angular momentum quantum number is your sub-level within a main energy level that also indicates the shape of the orbital. Now, to get into this, we have a lot more within the angular momentum quantum number. I'm going to pull up a periodic table. You need to have a periodic table out and even just do a dummy version outline of your periodic table. So before we get into our values of L that go with the angular momentum quantum number, we do need to outline 4 different what we call blocks of the periodic table. So starting off, we have what is called the S block. The S block is going to be groups 1 and 2. That also includes helium. That is our S block. Right in the middle, we have the D block. D block is going to be groups 3 through 12. And off to the right, we have the P block. P block is groups 13 through 18, but again, helium technically is over there next to hydrogen as part of the S block when we're talking about blocks. So again, that is the P block, groups 13 through 18. And there at the bottom, this section right down here is the F block. That is the F block. You will need to commit these areas to memory, so S, P, D, F, and what groups are actually within each of them. With this, our values of L. L can be 0, 1, 2, or 3. If L is equal to 0, that represents the S block. If L equals 1, it represents the P block. If L equals 2, that's the D block. And if L equals 3, that is the F block. So this is the sub-level designation that goes with each of the 4 values of L. Now, for the angular momentum quantum number, we said it also indicates the shape of the orbital. An S sublevel, its shape is basically a sphere. It's a sphere. For the P sublevel, we say it looks like a dumbbell. For the D sublevel, most of them kind of look like a 4-leaf clover. And then for the F, we don't give anything with it because it gets quite complicated. But I am going to show you some pictures that are also in your book. So we've got our axis coordinates set up. Notice we are working in a 3-dimensional region. So we have the typical X and Y axis, and the Z axis gives us that 3rd dimension. So the S orbital again is shaped like a sphere. And right at the center point of that, that's where your nucleus is going to be, where your three axes, X, Y, and Z, intersect. For the p orbital, it does look like a dumbbell. And for the d orbital, in general, is going to look almost like a four-leaf clover. And your nucleus is going to be there in the center of each of these. And your electrons, if you're talking about how do they actually travel, if it's an s orbital, it does look like they are traveling in a wave-like motion in a circular type pattern. But for the p orbital, your electrons are traveling in one lobe here and in another lobe there, and then the similar for your d orbitals. And one more thing to add to this, once we start talking about sublevels, shapes, we can also add on the number of orbitals. So again, our orbitals are the types of orbitals we have are s, p, d, and f. But an s orbital, because it's a sphere, it does not matter how you orient it around the axis. A sphere is a sphere. It's going to take up the exact same location. There's just one orbital associated with it. With the p orbital, you can also think about the one that's in green in the picture is along the y-axis. We can have another one along the x-axis and a third one along the z-axis, and they're all in a different region of space. So those orbitals, there are going to be 3 p orbitals. For your d, it gets much more complicated. If you could visualize it, there's a nice program out there on the web called the Orbitron. But the d sublevel has 5 orbitals associated with it, and then the f has 7. So notice 1, 3, 5, 7, there is a pattern there. That is the number of orbitals within those particular sublevels. So the number of orbitals that have those particular shapes, and f gets even more complicated than what we're looking at, those number of orbitals within a sublevel. Remember though, we were looking at the angular momentum number, which is that L value. So if someone said, oh, this electron's L value is 2, then you know you have to be on a d sublevel, and there are 5 different possible orbitals that L equals 2 could be referring to, because there are 5 orbitals within a d sublevel. Moving on here to the magnetic quantum number. This is our third quantum number, designated by the symbol M, and it represents the orientation of an orbital around the nucleus. So that XYZ axis that we just looked at, how is that orbital oriented around the nucleus? We have values that go with M. We're going to cover those right now. So M can be equal to -3, -2, -1, 0, +1, +2, +3. And here's how that translates to the other quantum numbers we just looked at. If you go back your S sublevel, and S sublevel only had one orbital, and that one orbital will only also have one possible value of M, which is 0. So if you're talking about an S orbital, its value of M is 0. If you're talking about a P sublevel that has 3 orbitals, those 3 orbitals have 3 possible values, which are going to be -1, 0, and +1. The D sublevel has 5 orbitals, and those 5 orbitals have 5 possible values of M, which are -2, -1, 0, +1, and +2. And then that leaves us with the F sublevel. The F sublevel has 7 orbitals, which means it can have any of these 7 possible values from -3 all the way to +3. We can get into specific orientations along the XYZ axis or a blend between axes. I'm not going to be that specific. This is definitely specific enough at this particular level. And our last quantum number is the spin quantum number. The spin quantum number only has two values, two possible values. It's either plus a half or minus a half, and that indicates the spin state of an electron. So when we start talking about these orbitals, you'll see later on we'll just use orbital boxes to make it very simple. This gets ahead a little bit, and you'll find out in section 3, but 2 electrons can live in one orbital, and that's the max. 2 electrons can live within one orbital. But if those 2 electrons are living in one orbital, they must have opposite spin. And that's why you see the 2 values that you do. So we use arrows to represent the electrons. An up arrow, we're going to say, is a plus 1/2 or a clockwise spin. A down arrow is going to represent the second electron, or the negative 1/2, or a counterclockwise spin. These two also, we'll talk later about why do they have to have opposite spins. I'm hoping you're making a connection about 2 electrons having the same charge, living close together. You know they want to repel, so something has to happen so that they can live close together and not repel. So there are your 4 quantum numbers. I do suggest you get them all out on a piece of paper and label it up back to back to back instead of in multiple places on multiple pages. This right here is just a quick picture. Again, your s orbital, the sphere, can only have one orientation. Your p sublevel has 3 orbitals. There's their 3 orientation. There's the d sublevel. A d sublevel has 5 orbitals. 4 of the 5 kind of look like a 4-leaf clover. You can see they are oriented differently along the XYZ axis. That 5th one kind of looks like a dumbbell with a halo around the center of it right here, and it also has a different orientation. But there you go. Again, F gets much more complicated. Now it's time for just a little bit of math. And we're going to look at the relationships again with these energy levels, sublevels, the orbitals themselves, the electrons within orbitals, to do some calculations so that we can find out, well, how many electrons can live actually within a sublevel and within an energy level. Starting off, your main energy level. What was that symbol we used for the main energy level? It was the letter N. The letter N. Well, it just so turns out that if you asked how many sublevels are within a main energy level, it is that same value. It is still going to be N. So if I said on the third main energy level, how many sublevels are there? Your answer would still be 3, since it's the third main energy level. And then we've got the next question is, well, how many orbitals can live on a main energy level? This time, it's a little bit different. It's going to be N squared. So if I were to ask you on the third main energy level, how many orbitals are there? Well, 3 squared is equal to 9. Our answer would be 9. And for the last one, getting to those electrons. How many electrons can live on a particular main energy level? And the calculation here is 2n squared. Now, your order of operations, you have to square n first, since that's an exponent, before you multiply times 2. So on your third main energy level, it is 2 times 3 squared, or 2 times 9, which is 18. So on the third main energy level, there are 3 sublevels. There are 9 orbitals, and there are 18 electrons, all within that third main energy level as far as where they can live. If we were to break that down into our SPDF, everything like that, so on the third main energy level, EL for energy level here. The number of sublevels that we have are 3, and those sublevels are the first 3 we talked about. So it would have to be S, P, and D. Those 3 sublevels are on the 3rd main energy level. And by the way, as I'm looking at my periodic table, the 3rd main energy level represents the 3rd period of the periodic table. If you were talking about the 2nd main energy level, that would represent the 2nd period on the periodic table. So, 3rd main energy level has 3 sublevels. They are S, P, and D. It says that there are 9 orbitals. If I go back to some of my math that we had earlier, I remembered an S sublevel has 1 orbital, a P sublevel has 3 orbitals, and a D sublevel has 5 orbitals. Well, 1 plus 3 plus 5 is 9 total. So there are the number of orbitals within each of those sublevels that live on that main energy level. And then when I go back and I add that last piece for the electrons, we said that each orbital can hold 2 electrons. Well, 1 times 2 is 2. 3 times 2 is 6. 5 times 2 is 10. Adding all of that up, 10 plus 6 plus 2 is 18. There's 18 total electrons that live within those specific orbitals of those sublevels within the 3rd main energy level. So this, very important. Make sure you understand that so you can do some simple calculations.